I'm Bruce Bugbee, Professor of Crop Physiology at Utah State University and President of Apogee Instruments. Today I want to talk about the work we've done over the past few years on measurement of precipitation. Now, this is becoming increasingly important all over the world as tiny changes of temperature means that the snow that used to fall in mountains now falls as rain. And boy, do we see that in Utah. This last year we had a lot of rain in the winter, even in the mountains, and now our snowpack is gone. And every place that relies on snowpack in mountains has got big issues with this. Rigorously quantifying the moisture from month to month, from season to season, from year to year. We've done this historically with tipping bucket gauges, but they can't measure solid precipitation, so we heat them. Fine, but that takes a lot of power. At remote mountain stations, where are we going to get the energy to heat the snow in the middle of winter and snowstorms? So we bring in weighing gauges with antifreeze, and now we have multiple companies selling weighing precipitation gauges. And this is what led the Utah Climate Center to initiate quite a large study of studying these gauges. And that's what we're looking at right here. We've affectionately called this thing Stonehenge because it's round and it's got so many pillars of gauges. I want to summarize the data that the Climate Center has been seeing from this. They're the ones that have organized this whole effort and put the data on their webpage. They, of course, have a huge network of weather stations with a mix of precipitation sensors on them. So they're keenly interested in this data. And like every state climate center, they share their results with other climate centers with what are they finding, what's working for them. So this is a picture with a webcam that's on the internet, so everybody can watch this in real time. And there are 12 sensors in this study. Now, the next slide, I'll show you a list of the sensors, but here's one. Let's see if I can do my pen right here, and we'll get blue. 1, 2, 3, 4, 5, 6, 7. Am I missing any right there? And then there's a tipping bucket right there, and there's another one over here. There's a dozen sensors in here. Some of these are heated tipping buckets, some of them are weighing gauges, and we'll work through that. All of them are heated, so they all are capable of measuring snow, either by weighing it or by melting it and measuring the tips in this. This has been a really great data set. The World Meteorological Organization many years ago did the SPICE program. They did tests like this, but I'm not aware of other people that have gathered this many gauges in one place to do a very rigorous intercomparison among gauges. You'll notice over here, this gauge has an alder shield around it to calm the wind. That's huge, that's important. We don't have that fence up here. It'll look like this. It'll be a fence around the whole thing. The good news in Utah is we rarely have blizzards with high winds. We get frequently gentle snowfall, so calming the wind for us is less critical. This is a test of the gauges themselves, not the gauges plus techniques to calm the wind. Not that that's not important, it's just not part of this test yet, it's just the gauges. So let's take a look at which gauges we have. Here's a list of the gauges, and you can pause this and study them on your screen. You can see over here we have 3 heated, 5 heated, so 7 of these use antifreeze and weighing, and 5 of them use heat to do this. And we're not power constrained. This site has 120 volt AC power. We just use the power to melt the snow. There's several replicate Apogee gauges in here. We have a Geonor gauge, a Lambrecht gauge, a MET1 tipping bucket, MPS. Here's the Pluvio. Here's the PreciBal by KISTERS, and 2 replicate Texas Electronics gauges, which are tipping buckets. These are widely used because they're low cost. So this test helps us see how all of these work. So now we go to the graph on the internet. And this is a quick graph. It doesn't summarize the data yet. We had some rain last week. We don't get a ton of rain. This is only 4 millimeters. It rained really hard right here. The gauges are really close to each other, and then we got a little bit more rain, and they're close to each other. This is one rain event out of 100 that we accumulate. You can see 2 things from this graph right away. This green line isn't 0. You can see this fluctuating around. Not a ton, plus or minus 1.5 millimeter. This line is the Geonor gauge, and this gauge is not fully compensated for changes in temperature. So when it's hot and sunny, it reads a positive number and then it cools. The other gauges, the other weighing gauges, have algorithms to take out this effect, measure temperature and take it out. So the other gauges all read a clean 0 when it's not raining. Now you can see when it rains, that happens here too. So the Geonor in this particular event ended up pretty close in spite of this. But that's one of the findings of this. That's a characteristic of the Geonor gauge. The Climate Center purchased all these gauges new from the manufacturer. This line right here is low, not a ton, but it depends on the accuracy. That's maybe 20% low. That is one of the Texas Electronics gauges. And generally, we've found those to be slightly less accurate, even in measuring rain. One was right in the middle of the pack, and another was slightly low. But these are what you get with rigorous tests with replicate gauges when we do this. Now I'd like to show you some of the long-term data. This came from a precursor of this site where we had 1, 2, 3, 4, 5, 6 gauges with the snow fence. And this was a little over a year, a 15-month study. About half of this study was snow, and about half of it was rain. And I want to separate the accuracy for snow from the accuracy for rain because they're quite different for these various gauges. Let's look at the data. Here's a graph of a year and a half. Here's the 4 weighing gauges right here. And the MET1 375D is a high-end tipping bucket gauge. We powered this gauge so it melted the snow. So we go along for winter. Here's winter right here. And what you can see from this line is when we were melting snow, that gauge tended to read low. And we get to right here, and it's slightly low. All of the other gauges are very close to each other. So let's look at the digital data for this. Oh, and then we added the Texas Electronics right here in the study, midway through the winter. And that one started to get a little bit low as well by the end of the winter. So now we have 2 tipping buckets. Here's the data. All of the weighing gauges within 1% of each other. I consider that quite remarkable accuracy, cumulative over the winter. The MET1, 14% low, and the Texas Electronics was only there slightly less than half of the winter. This might have been, maybe as much as, let's see, minus 12% low had it been there the whole winter. Again, presumably because the heating mechanism causes some evaporation of the liquid or the solid as it melts and evaporates, and it doesn't fall in the tipping bucket. So You could argue you could do corrections for this, but that gets tricky when you're trying to do corrections for different environments. So let's now look at the next part of this data, which is the rain. So here we are, spring, rain. Now this gauge was slightly behind here. It's still behind. But when we take just the rain, all of the gauges, now they're all within 2% of each other. And this is a lot of liquid. I mean, it's a lot from here to there as the cumulative error was small. It shouldn't be surprising that tipping buckets do a fine job of measuring rain. That's just liquid water that falls in the gauge. It's the challenge is right here. It's measuring snow, even when you melt the snow. Now over here, I want to show you the cumulative data, and there it is. It was 467 millimeters over a 15-month period. Again, all of these gauges are really close to each other. This number might be -7 if we'd had that tipping Texas the whole winter. But the important point here is the rain and snow. It's just really difficult to melt snow accurately and measure the water equivalent. I want to make a key point. There is no NIST standard for this, so what we did to get these numbers was take the average of these 4 sensors. They're really close to each other. We just averaged all 4 to each other, and we considered that a reference standard, which is why these are not all 0. It's percent from the mean of those 4 sensors. This is how we got this data. Now, we're rapidly accumulating a lot more data from our Stonehenge site right here to go back to the first gauge. More gauges, more length of time, more snow and more rain events. I want to give a credit to the people at the Utah Climate Center for assembling this data, and also to Mark Blomquist for helping collect and summarize all the data. It's a group effort of people doing this. We're real excited to see how this comes out. Not only the immediate accuracy, say in the first year, but the first 2 or 3 years, if they're accurate, do they stay accurate? All of these companies have put a lot of R&D into making high-class gauges, but in a world that is so water limited, it becomes increasingly important to get a precise seasonal estimate of moisture, not just rain in the summer, but snow in the winter. Thanks for listening. We'll talk to you again in the next video.